It is really my great pleasure to introduce you Shupira Chakrabarti, Professor of Physics and Director of the Lowell Center for Space Science and Technology. He is also a specialist, or is a specialist, in space experiments and hyperspectral imaging. Shupira is a Bachelor in Engineering in Calcutta, in India, but he developed all his career in US with a PhD in University of California, Berkeley in '82, and where he was also a senior fellow as faculty member. In '92, he moved to the East Coast, to Boston University, and he served as director of the Center for Space Physics. In 2012, Professor Chakrabarti moved to Massachusetts, to University of Massachusetts Lowell, with his group, where he develops instrumentation for assessing carbon content in forests, solar terrestrial interactions, and direct imaging of exoplanets, and he really conducts lots of scientific studies of galaxies and upper atmospheres. He has been involved in several projects since his initial great achievement with his sound rocket payload for auroral studies, and also involved in the Apollo-Soyuz program. And very recently, he got an interesting grant from NASA, almost 6 million euros, on a project called Picture-C for detect young Jupiter-sized planets orbiting stars in the Milky Way. So his present interests are exoplanets, interstellar medium, and planetary atmosphere. But as he quoted in a recent interview, his goal is to discover Earth-like planets around Sun-like stars capable to supporting life. I had the chance to visit his lab at Lowell University, and more than a brilliant scientist, Shupira is a professor with a bold name, a professor that leads and motivates students, fostering a spirit of knowledge-based discovery, and also with a remarkable hands-on approach. So this is why we count with Professor Chakrabarti to help UMass in our new aeronautical and space ventures, and this is why I'm sure you will enjoy very much this talk. Shupira, please.
Thank you. So thank you very much. I'm sorry, I only know 2 words in Portuguese, vinho and cerveja. I think vinho means thank you, and cerveja means please. Those are the 2 words that Professor Cunha taught me, so that's what I'll try. So thank you. Please be patient with me because I may speak too fast. If you have any questions, please interrupt me, and I will try to explain. So as Professor Cunha mentioned, our research group moved to University of Massachusetts in Lowell. But before that, in the early 2000s, we started sort of asking the question. And these questions are, we know historically space explorations were done by countries, nations. And then we started thinking there have been a lot of technological advances that has happened. So why doesn't every university build satellites? Or why doesn't every company build satellites? So these are the kinds of questions. You can sort of read them what they are. And then it also related to that is, where do we get people who will build the next generation of satellites, or who will become next generation of space explorers? So through that, we wanted to be an institution where we could do technological research, we could train students, and we'll try to develop these technologies in some small sense and validate them in space. So that was the goal. But it's not just us. We decided that we should hear from great minds. So in 2007, to commemorate 50 years of Sputnik, we gathered a group of people. And if you look in here, you'll find a Nobel Prize winner in physics who got their Nobel Prize only a few months earlier, somebody who walked on the moon, the man on the right, he walked on the moon. There were 2 Apollo astronauts, somebody who's fixed the space telescope, and so forth. But more importantly, what happened was those 2 men on the right-hand side, they started a company soon thereafter. This was happened in 2007. In less than 5 years, they started a company at that time was called Planet Labs. And that same company, one company, now it's known as Planet, they have launched more satellites in space currently than any other. In one launch, they have 98 satellites that were launched. So the landscape changed. In fact, in the same, there are link URL links. This program was addressed. The keynote speech was given by the president of India at that time, who, as a young man, was involved in space research. So he addressed that. And so there are many things, but the landscape has certainly changed, and these are now a list of how many satellites have been launched per year, 2012 to 2017. And what you find are the largest number of the satellites that have been launched are in the category called small sat, which are highlighted in yellow. So these are the number of satellites that are being launched. And as you can see, the trend is clear. There is going to be a larger and larger number of satellites that will be in space. And so the question is, who is going to do it? Well, you could also get a hint of that, and you find that most of these things are being done by companies. But the second most things are being done by universities, not very different from where you are sitting. And so then there are others, if you look at them, universities, institutes, nonprofit, even an individual. There has been an artist in Japan who built his own satellites and flown. So what does this mean? That means that space is now open. It's completely democratized. I think I heard that word earlier today, even though it was spoken in Portuguese. I figured that one out. So we also held another gathering. This was in 2017. Again, to find out from people where we should go, what we should do. It had, again, 3 astronauts. In the middle panel, the man in the middle was responsible for the American Star Wars program. So we had many different types of people. In the first one, we had somebody from the Vatican Observatory. And then we had people who were astronauts. There were 3 astronauts and somebody who currently is the director of Space Telescope Institute. Even more recently, to commemorate 50 years of moon landing, we had this program where we had the chief scientist of NASA, a private company who was competing for Google X Prize to land something on the moon, and then others. But the key here is the man second from the right who invented something called CubeSats. How many of you heard of that term? CubeSats. So many, right? So that's the man who invented, and he came and talked to our students and described things. Well, for the 2 people who don't know what CubeSats are, these are 10 centimeter on a side cube, and you can put them together, multiple of those, and then that could be 1U, 2U, etc. And so there are many examples like that. So that's a 1U CubeSat. This would be a 2U CubeSat. And the limitation of what you could do with them is really limitless, basically. It's your imagination will determine where you can go. And then you could ask, what are they doing with these little things? And if you look over there, there's technology, science, engineering, education, and also communication. So there are many things where this university excels in, can participate in. So I think that these are the kinds of things that we could think about. And even more, as I said, this was democratized. If you look at it, the largest number which are given in this yellow are the universities. So this is where I think we can train the next generation of space explorers. You can design, build, fly, and I will try to convince you that it can be done. And so there is an article that I wrote in here, and that sort of talked about how it's got started from something called Beanie Babies. It's this thing that came in a clear plastic container that had a 10 centimeter on a side, and that was the inspiration of Bob Twiggs in coming up with the size of that. And it turns out that size gives you 1 liter volume. You get roughly about 1 kilogram. So that's the standard that has been set for CubeSat. Now, to do anything, you have to have also the same kind of, what you want to do has to match the vision of Portugal. And we were fortunate that the vision of Portugal in space has been articulated by Minister Heitor. We're very grateful that he came, visited us. There he is, being a fashion model, holding one of our research center's bag. And in here, what he pointed out is the next generation of satellites is a priority. Miniaturization of satellite platforms is a priority. Constellation of satellites is a priority. And finally, utilization of space for the benefit of humanity. These are perfect goals for an university where the education and the development of next generation of explorers. So we're very fortunate. And we also know that this is one of the programs that's been articulated and being developed, which would be a constellation of satellites for communication and also environmental monitoring. So this is where the goal is. So now I'll try to convince you that with that goal in mind, universities in Portugal, especially here, are poised to do great things. So I'll try to describe some of the things that we have been doing at the University of Massachusetts. I'll try to go through this thing rather quickly. Some of the features that are involved, we recognize that to do anything like this, you need to develop tools that do not exist. And this is a tool that we have developed, and you'll see that students are involved. These are to image trees in a forest to count for how much carbon is in a forest. And this is done using a two-color LiDAR or LiDAR. So we have developed this. Here is a forest where there are leaves in Boston area. After a winter snowstorm, the leaves go away, so we can calculate this and image them separately. We can talk about this later if we're interested. We also use the tools that we develop to study Earth's upper atmosphere and try to understand what happens when there are activities in the sun. How could that affect satellites and other technological assets, both in space as well as in ground? So-called space weather. So we have developed something. In the middle, in this panel, are some. The x-axis is time and y-axis is location in the sky, and color gives you the brightness. In this case, we see a time when there is an aurora that we see, the next day when we don't see an aurora. So you can sort of see we have these tools that can be developed for many different applications. These are optical. In our center, there are other people who do all kinds of computational work, using latest tools, and then over there, we're in astrophysics, so that's people study black holes, etc. We also are a center where we involved technology. So there are people who develop various sophisticated materials that are self-healing in space. That's an important aspect of it. So those are things that we do. We also provide hands-on experience. We find that the way to learn is by doing something and making mistakes and then learning from that. So we built an experiment, or they flew, this is in 2010, and a balloon. These balloons are very large, larger than a soccer field size in the long direction, if you assume their diameter, and they could take a small car, maybe 2 or 3 small cars, up to about 40 kilometers or higher. So you're above 90% of the atmosphere, and you can do some major research. And we just flew an experiment on September 29, and I'll show you what we did with that. So these are some photographs from that balloon in India that was to study Earth's upper atmosphere. I also know that there is a strong aeronautics work here. This kind of platform also provides an opportunity to test your instrument in air, so far from you, before you get to space. You could test that. So with the BAE, as a big British aerospace company, we have developed and validated some of their technology. And then, of course, rockets. We design, build, and fly experiments. This is typical PhD program in my research group. These two are two PhD students. The way we train them is the younger student help the older student and in the way learn something. And then the next rocket flight that we get, the younger student become veteran enough to fly their own. In this particular case, you fly that, it comes down on a parachute, you go on a helicopter, recover it, make some changes, and fly it again. This is a perfect vehicle to design and test your electronics or technology before you put in a satellite mission that are hundreds of millions of dollars. The other thing we do is we also have orbital missions. We designed an experiment. This is a hyperspectral imager, but it works in the ultraviolet. It's currently flying on the space station. And we designed and built it and flew it on a rocket before. Once it came down, we validated its performance. There was an opportunity to put something in the space station. So we're fortunate that we're selected for that. And those are the pictures of the instrument in the space station. Now, the other thing is we also work on important problems. Some of you probably recognize this scene. This is the opening scene from Harry Potter movie. Anybody remember what happens here? That man, Dumbledore, right? He had a thing in his hand. And that instrument is called the illuminator. And what did it do? It turned off that light. And we built that illuminator and we flew it. So I'll show you. So this is what it does. You turn off that light, and the reason you want to do that is you could see things around it. And why you were doing it? Well, our goal is to try to take pictures of planets around nearby stars. But the planets are about 1 billion times or 10 billion times dimmer than the star. And the stars are also bright, but because they're far away, they're very faint. So the whole thing is dim, and then in angular space, they're all right on top of one another, just like two car headlights look right very close to each other in space, in angle, when they're far away. So what you have to do is turn off selectively or dim the light of a star so you could see the effect of the starlight on its surrounding. So we built and flew this thing on a rocket. That thing is the optical design. I'm not going to talk about it. If you ask me, I'll be happy to tell you about this. So we built all of these things. It has to be very lightweight. We launched it twice. And another thing you have to do is when you're pointing at this star, you have to hold it very steady, because if it shakes, that billion times brighter thing will overwhelm the light of that tiny fraction of the planet or asteroid belt in this case. So you have to do all of those, and you need a perfect telescope, which nobody can build because we are humans. So you build something that corrects it. Over there is an animation. I don't have much time, but what it does is in real time, it corrects for the deformation due to thermal stresses or imperfection in building it. And so you could do that to correct for them. So all of these things has to happen simultaneously to make it work. So that's the challenge. And we're trying to do these things. I was part of a NASA study where we studied a system like this that's $1 billion mission on paper. And we're demonstrating all of these things in a small group. So this is what we did. we are building this thing on a balloon. This is a balloon roughly about 3.5 meter long, the experiment, that bridge-looking thing. And it had carried a 60 centimeter diameter mirror. That's the primary mirror of the telescope. So our instrument is now about a 1 meter square and a 3.5 meter long. And this whole thing weighs, with NASA support, weighs roughly about 3,000 kilograms, 6,000 pounds. And that's what we flew on September 29. And here are some pictures from the field. This whole thing, without this wheel, flew. On the right is how it's connected to the balloon up there. So you can see that crane-looking thing. That's where the balloon gets connected. The problem with that is you cannot look straight up, because that's where the soccer field or football field size, about 400 feet in diameter balloon is. But nonetheless, you take it. This is we launch it at about 7 a.m. So this is getting ready at 3 a.m. in New Mexico, Fort Sumner. And now we're getting ready to launch. And then that picture is taken. We had a camera on the balloon looking at space. You can see that the sky got dark. It's black. Because you're above most of the atmosphere, now sky is dark. So we launched this thing. We collected some data, about 8 hours of nighttime. So you launch in the morning, stay up all day. So that picture was taken during the day. And then after the sunset, we started taking some astronomical data. So this was an experiment to demonstrate the technology works. We believe we have validated key technologies. We are going to fly it again next year. It came down, and we are very fortunate that most of the things came down very well, so we did not have to do a lot more refurbishment. So that's one of the things we are doing, and this particular work, the key people are 4 people, a scientist and an engineer and 2 PhD students. There are other help, but those are the 4 people worked on it for about 5-6 years to make this work. Now, the other thing we're doing is our undergraduate students are currently designing and building a CubeSat. It's a 3U CubeSat, and it's going to demonstrate high bandwidth communication. So you can sort of read all of those, but 50 to 100 megabits a second is factor of 10 to 20 times more data than current CubeSats can do. So our students are trying to demonstrate that. Our plan is to launch it next year. So undergraduates, they have designed, built it, they will operate it, and they will analyze the data. The other thing we can do is we can show you how quickly we can do things. Somebody gave us a challenge of building an instrument that could do remote sensing, and we started with this. The day somebody said, can you do that? We go and find things in our lab saying, can we use that? And of course, we have engineering students, they could do things. We have done the optical design to fit all of this in that space. We built it, and I think Professor Cunha, you saw when you came to Lowell this instrument in operation. So that's the scene. Lowell is very famous for their textile work, and so our lab is in the textile mill like this, and this is looking out. And what you see here are in 4 different colors. The room is pretty bright. It's continuously looking at the sky, and you can see there are now street lights at night time. Street light happens. So what you see here are the data that we collected in more or less real time. But we didn't tell NASA, and we took this instrument, put it on the balloon. And so we flew that, and this is a picture of when the balloon is getting ready to be launched on the ground, same 4 colors. And then over on the right are 2 examples of taking things from 2 different heights. You can sort of see people in there come in and go. So this is how we do things. So there are features of what we have done. We are at a university, not very different from yours. Now it's launched. I can sort of see as it moves up, it's still looking sideways on the balloon. So I thought since we're here, we're talking about it, how we could think about possibly working together. And so what I did was I went and started looking at what has been done. We know that there has been a study about setting up a launch operations in Santa Maria Islands in the Azores. And there are several companies that were asked to do various studies. And one of the results that came from the MT Aerospace, it talks about the altitude of the orbit in kilometers, and then how much satellite mass you can put. This is the study that was done as a result. That line shows that there are two different regimes that people are considering. One is in here, where you can sort of see things are mostly optical remote sensing work, and the above that are mostly communications. So these are studies that has been done. Of course, there has been also a study by Ariane Group, same in response to that. What you find are they broke this thing into different categories. Class 4 is 1 to 25 kilograms. That's sort of university level perfect because things has to be small. And then it goes up to about 200 kilograms. And then if you look at them, you can sort of see there's a standard, there's an education, and there's a constellation. So those are the key. And just like the minister talked about constellation, just about the minister talked about developing trained workforce. So I think that if you do the counting, they're talking about in a period of 10 years that the study concluded that there will be 400 to 500 satellites that will go up. Of that, 40% will be in the smaller category. So that's where the largest number are. If you then look at how much of that 40% could be contributed by education, 15%. So this is a very healthy number, perfect for the university. So that's what I think one can do. Ariane Space looked at the cost of launches. And again, they have a similar thing as the MT Aerospace, but they have a slightly different numbers. Launch costs have gone down, and they have looked at different types of launchers. So now if you look at these, you can sort of see that they already have different launchers already developed that are ready to launch things that are small sizes. And then you can start asking questions where you could find areas of work. And this is not my work, this is Ariane Space, so it must be right. If you look at education and capacity building, just look to your right and left, you find the people who will benefit from this. If you want to look at startup or launch services, there are lots of small companies that were present here today. So you can sort of see the timing is right, the background that you need is right, everything that you need is here. Finally, in Europe, there has been a program for QB50. It's a CubeSat, 50 CubeSat constellations that was launched. And so there are examples of successful programs that are all here. Finally, we find that we have similar interest. If you look at the list of projects, you'll find some of the things that are something that we're talking about here. And also, the infrastructure is already available. So it should be relatively straightforward, not easy, but path is straightforward to develop programs in aerospace engineering here. And I can give you an example of what we have done. At my university, there is no aerospace engineering degrees, but we're just started a aerospace engineering minor. One of the things we did was I taught a class about designing a small satellite. This is, as a part of the class, some student went and built a whole model of what they were proposing. The purpose of the class is to design a proposal, and this was not required to do. And I also want to point out that it's not just college students or university students. School students are in there. Here is our examples of high school students that have built and flying satellites. Israel is on their third thing. But this is high school. If you really want to know younger students, you have to go to Brazil. Those are middle school students. They have built and flown satellites. Imagine 6th, 8th grade students. And that's the picture of launch from the space station. So the point is, there are plenty of examples of young students, school students, middle school students. So if they could do it, clearly the environment is ready for all of that. So, of course, I always look towards others for guidance. This man was the head of India's space program. And there are many others in here that you could find. And this photo was taken 2 days ago in Lisbon. And so we're very fortunate that there are many, many people who can guide us. So my point is, there are the right background, there are the right people, the timing is right. We should be able to develop a space program together involving universities and small companies. So that's the summary, and with that I should say thank you very much. Obrigado.
Okay, thank you very much. Thank you very much. I think all of you noticed that we had the chance to benefit from pictures of the experiments that were done 2 weeks ago, and so we saw the images of these launches with these balloons, and so it's very, very new stuff that you shared with us, so thank you very much. So, any questions for our speaker of this afternoon? You have one over there.
With the exception of time and travel distances, what do you think is going to set that to colonization in other worlds?
Building things, if it breaks, nobody will care. If you launch anything living, whether it's animal or human beings, things are a lot more challenging. Supporting life is a lot more difficult. But we have been to the moon. We're talking about going to Mars, and that's the next big thing that even private companies are competing for their priorities. In the US, Blue Origins and SpaceX, they both have their plans of going to the moon. Going to Mars. So I think it'll happen. Probably not in my life, but certainly in your life, and probably somebody who will walk on Mars are probably one of you probably sitting in this room. So I encourage you to think about solving the necessary problems, but some of the problems we don't know what they are. So I don't know enough about this to even comment what the setbacks would be.
I'm going to be a little bit provocative, because I heard a statement of the IEU about satellite constellations. A lot of them could be a problem. Are you thinking on how to mitigate that problem? Are you thinking on not too many, not too a lot of them? How is the time of a lifetime of a satellite like this? Are you thinking about that too?
Yes. There are a lot more smarter people who are thinking about it. We do know that there has already been a problem with some of the larger satellites, not CubeSat, but larger satellites, leave a streak of light in the star field. So it's a problem for astronomers. So Right, I'm aware of that. So that's a problem. At the same time, the other thing that you're talking about, and how long they stay up. Anything that we design and build and fly, NASA requires that they must come down in 25 years. So for the smaller satellites, if you are putting them in low Earth orbit, there are probably high probability that they will come down, or you can send them away. There are people who are thinking about it and doing whatever necessary to do it. The thing is, we need this as a world community to think about it. The UN has an organization, UN Office of Outer Space Affairs, right? So I think we should follow those. Just like somebody told me one time, the best rules are they're easy and everybody understands, like the two yellow lines on a road. Everybody knows you're not supposed to cross it, and most people follow that. And if we could do something like that, I think that'll be a great thing to do.
So if everybody is happy, I think we should thank our speaker, and we'll move on for the next.